up a couple of brain exercises just to get us all warmed up today. Hopefully this is going to be comfortable for you guys based on what we covered last time. And hopefully you guys have actually practiced a little bit of this, or at least reviewed the slides from last time. So these brain exercises shouldn't take too long, but I want to kind of give everyone a chance to think about it on their own for just less than a minute, and then we'll kind of go at it together, okay? Okay, so how many valence electrons does carbon have?
4.
4, perfect. That is exactly right. There are 4 valence electrons in carbon. We know because we can read it right off of the column of the periodic table. Let me get my laser pointer going. Here in column 4A is where carbon is, so it has 4 valence electrons. How many total electrons does carbon have? 6. A lot of people are putting it in the chat. That's great. That is the right answer. There are 6 total electrons that carbon has, because in addition to its 4 valence electrons, it also has 2 valence electrons in the 1s orbital, which are not part of the outer shell. So 6 total electrons. How many protons does carbon have? Yeah, I got a couple of 4s and a couple of 6s. So carbon has an atomic number of 6. That means it has 6 protons. So I cheated a little. The little partial periodic table that I gave you guys here does not have the atomic numbers listed, but you can see they count upwards in terms of numbers of protons. So 1, 2 for helium, 3, 4, 5, and 6 protons for carbon. You also could think about it, another way to think about it is that you just told me carbon has 6 total electrons. And if I'm asking about neutral carbon, which I will be unless I specify otherwise, then those 6 electrons have to be balanced by 6 protons. So 6 protons, 6 electrons total, and 4 valence electrons. How many valence electrons does fluorine have?
7.
Yep, 7 valence electrons because it's in column 7 of the periodic table. And how many total electrons?
9.
Perfect. So in addition to those 7 valence electrons, there are 2 electrons hiding down in the 1s orbital. And finally, how many protons does fluorine have? Protons only. How many protons does fluorine have? Yep, it's got 9 protons. Those 9 protons and the 9 electrons mean that fluorine is overall neutral. Okay, so we will tend to use the periodic table a bit in this class. Most of the elements that we're going to use, you guys will kind of get to know, and you may not need a periodic table with you. In case you want to look at a periodic table, I just emailed the class one a couple minutes before class started, and you can also find it on Canvas. We don't have the benefit of being in a classroom where I can point on the wall and use my laser pointer to show a periodic table, and I don't have enough space on my slide to always have a periodic table. So if you guys want it, I suggest printing it out, having it next to you. There's also one in your textbook. You will be provided with one on an exam, always. But yeah, okay, well, let's get started with other stuff. Just a couple of reminders. Email is the best way to contact me. I know I told you guys I would be caught up by emails by the end of this weekend. I am not caught up with emails. I still owe a couple of you emails, so please bear with me. There's a lot more of you this semester than usual. I'm going to start my office hours on Wednesday of this week, but don't forget there's an SI session this evening. So if you're having questions about the material, or if you want to do some practice problems that are targeted for the material we cover in class, you can go to this SI session. I believe it's in Hibbs 118, but check my slides from Friday for that exact location. A few other announcements. I am going to be posting your first graded Achieve homework. I will be posting it probably later today or tomorrow. It'll be due Monday at 9 a.m. If you still need to sign up, here is the link. Someone has asked how participation grades are graded. We'll get to that later in the class, so just hang on to that question for now. But this Achieve homework is a graded homework that counts under the graded Achieve homework part of your grade. You can check the syllabus for more on how that works. Also, under Canvas, I want to make sure you guys are comfortable getting to know Canvas and finding your way around in Canvas. So I just wanted to toss up this one screenshot. Most of what you are going to want to find will be under the modules. There's also a link to the modules on your homepage when you click on your course from the dashboard. Here you can see chapter 1. This is what the Canvas page looked like when I was prepping these slides. Now you will additionally see a periodic table down here at the bottom. And then when we get done with class today, probably later this evening, actually, I'll be posting the slides from today and you'll see them here. So the modules are going to be one place to find things. And then also assignments is going to be another place to find things. But of course, all of these tabs are useful and you can look around for the rest on your own. Okay. So we are in the midst of chapter 1. We got a good start to it on Friday, and we're going to keep going with, we'll pick up today with the octet rule and keep going from there. Before we do that, I just want to refresh everybody's memory to somebody's put in the chat, yes, Achieve will also be used for Orgo 2. Okay, sorry. All right. So I want to refresh everybody's memory from where we left off on Friday. So just as a reminder from last time, we talked about the first couple of orbitals, the first lowest energy orbitals, the 1s and 2s spherical orbitals, and then also a set of p orbitals that are equal in energy to each other. So they're the same energy as each other. That makes them degenerate. And also they're oriented, each one of them, along a particular graphical axis. So when they are superimposed, they don't overlap at all. Sometimes you'll hear me say the word orthogonal. That's what that means, is when they don't overlap at all. And we also talked about how when you fill up these orbitals, you have to fill them from the bottom up, so lowest energy first. And when you encounter areas like degenerate orbitals, you have to fill in one electron at a time before you go back and start filling the next set of electrons. So you got to have 1 in all of the p orbitals before you have 2 in any of the p orbitals. And if you look at my slides from last time, you'll be able to see the annotation that I did during class. Also a reminder from last time, and this is where we left off, just thinking about organic chemistry, the whole point of organic chemistry is that we want to be able to understand the electronic structures within molecules and be able to use that to help understand and predict the 3-dimensional structure of the molecule, the reactivity of the molecule, and all of these things. So electrons are really what makes everything happen. That's the action end of a molecule. And in particular, the valence electrons, so the ones that are farthest away from the nucleus on the outer shell, are going to be the ones that we're interested in. I gave you guys this table out of your book that shows the electronic configurations, which you guys will need to know how to write in using this annotation. And also we talked about the valence electrons associated with each of the first elements and kind of the first 2 rows. We talked about how carbon is going to be the most important one for you guys to remember, especially that carbon has 4 valence electrons to it. And as always, you will always have a periodic table. You will always be able to refer to that. The number of valence electrons is the same as the column in the periodic table. So in addition to carbon, which we should all be really comfortable with, we also are going to spend a lot of time covering the elements in these blue boxes. And this doesn't mean you're off the hook for the rest of the elements. The other elements can show up. Most of the time, though, we're going to be working with the elements contained in these blue boxes. And if you encounter one of these other elements, you just go back to the periodic table and use what you know about why carbon has 4 valence electrons to figure out how many valence electrons other elements might have. Okay, so now I want to get into the octet rule, which is going to be the next kind of section of your book and the next section of slides here. So we've already talked about how important electrons are for organic chemistry, how that's where all of the excitement happens. That's what we need to understand to be able to understand all of organic chemistry. There is a cool kind of, when the people figured out the periodic table, figured it out, they didn't have any idea how useful it was going to be. And they just noticed some trends and they put some things together and they followed some patterns. But it turns out to be really useful and really incredibly helpful for understanding the electronic structure of atoms and also how that relates to molecules and bonding. So there is a stability with what we're going to call a filled shell of electrons. So what I've got here is a section of the periodic table. Here's the upper left-hand section, what's called the S block. Of course, the S block goes further down. And on the P block, that's the kind of the upper right-hand side, the right-hand side will go further down, all the way down. But we're just looking at the top couple of rows. So the S block and the P block together are where we're going to stay in organic chemistry. We're not really going to get outside of these two blocks. And you'll notice at the end of a row, you have the noble gases. These noble gases have 8 valence electrons. Does anyone know another name for noble gases?
Halogens?
No, the halogens are in column 7 right here. That was a good guess. But the noble gases are in column 8. Yep, inert gases, that's right. So the noble gases are also called inert gases, and they're called inert gases because they're largely unreactive. They're very stable. There's a stability associated with them because they naturally have a full shell of electrons. So in the first row here, a full shell just actually means 2 electrons. But in rows 2 and 3, a full shell here means 8 electrons because you have your 2 p electrons and then your 2 s electrons and then your 6 p electrons. So 8 total electrons. So most of the time in organic chemistry, with the exception of hydrogen, most of the time we're going to be dealing with second and occasionally third row elements. So in most of organic chemistry, a full valence shell is equivalent to 8 electrons. And it's now eventually kind of over the course of time has come to be known as the octet rule. So I'm going to pause for a second because there's a question in the chat box that I want to address. Someone has asked, is there a way we can get informed what topics we'll be covering every day? So before Zoom, we can review those topics from the book. I'm going to follow the flow of the book and the kind of the cadence of the book and the direction of the book for chapters 1 through 10 directly. So I'm not going to be telling you guys ahead of time what's coming up, but if you look at the beginning of my slides here, this is the set of topics in the chapter, and this is the set of topics that I'm going to cover in more or less, usually 99% of the time, the order that I'm going to cover them. So wherever we ended last time, you can pretty much bet that we're most likely going to cover the next couple of topics in the next class. So you can get that information. It's like self-contained in the slides. Did that answer your question, I hope? Of course, I post these slides after class. Okay, so back to the octet rule. Okay, so hopefully everybody understands 8 electrons to fill a valence shell. Again, hydrogen only needs 2 electrons, but you'll often still hear me call it an octet, even though it's 2 electrons. And here's a big key point in a box. I cannot emphasize enough how important this octet rule thing is. This is going to underlie and guide a lot of what we do in organic chemistry. It's going to be essential for knowing whether or not you've drawn a structure correctly, for understanding where the electrons are in a structure if they're not all showing to you on a drawing. Okay, so this is what we mean by the octet rule. Every atom in a molecule is going to do its best to try to obtain a completely full valence shell. So most of the time that's going to mean 8 electrons, and that's going to be called filling the octet rule. This is in essence a way to try to get a noble gas or an inert gas configuration. And how they do this, one way to do this is to transfer electrons from one to another. Okay, so what that means is that if you have an element such as lithium that is at the far left side of the periodic table, it only has 1 electron. It would have a long way to go to get up to 8 electrons. So instead of trying to get 8 electrons, it gives up an electron to get to the inert gas configuration that's just before it, which is helium. So that lithium is going to give up an electron so that it can then become lithium plus. And then it's going to give that electron to a fluorine. So fluorine normally has 7 valence electrons. It's in the 7th column of the periodic table. When that fluorine accepts that electron from lithium, that fluorine now has 8 electrons. That means it has a full octet. like a legitimate full octet with 8 valence electrons, and that's the same configuration as neon, an inert gas. Now, because in this case, one atom gave up its electron completely to the other atom, and the other atom accepted it completely, these two atoms, which are now ions, right, a lithium plus and a fluorine minus, these two atoms are now in an ionic bond with each other. They are ions and they're bonded, so therefore it's an ionic bond. So that's one way atoms have to get to an octet. If they're close to an octet already, oftentimes they will get another electron or give another electron up. Electrons can also be shared between atoms. And then in this case, you'll get a complete octet where a shared pair of electrons counts for both atoms. So it's not one giving it up completely to the other. And what this means, here are some pictures to help. They can be shared perfectly evenly, 2 electrons perfectly shared between 2 atoms, like in the case of hydrogen gas. And that'll give us a nonpolar covalent bond. If they're shared unevenly, so in the case of a carbon-chlorine bond, these 2 electrons are shared between the carbon and the chlorine. Each of these elements, the carbon atom and the chlorine atom, each of these atoms counts these 2 electrons as part of its own octet. So carbon has 2 electrons in a bond here and here and here. That makes 6 electrons, and it's going to count both of these electrons to get 8. And chlorine has 3 lone pairs, so 6 electron. It's also going to count these 2 electrons to get its 8. They're shared unevenly. They're closer to the chlorine, or I guess to be accurate, they spend more time being closer to the chlorine. But this bond is still covalent. Covalent means they're shared between the atoms. It's polar because they're not shared evenly. And just again, to draw that comparison with an ionic bond where there's no sharing, one atom gives up an electron and the other atom accepts it. I'm going to pause here and make sure nobody has any questions. Oh, okay. So how do we know what kind of bond it's going to be? Oh, well, yeah, you guys hopefully already knew this, but the octet rule, the goal of every atom to get a full valence shell is going to be what's driving this whole process. Okay, so how do we know if we're going to, make a covalent bond or a polar covalent bond or what? Well, that has to do with the electronegativity. You guys, I'm gonna not transcribe this because there's words that it gets wrong and it actually distracts me because it's popping up on my screen and I can't see my screen. So I'm gonna not use transcription, but hopefully you guys will be able to follow along with this, and hopefully you'll also be able to solidify these concepts by reviewing my slides after I post them in combination with your textbook. So how we figure out whether a bond will be covalent or ionic or polar covalent or non-polar covalent, and we'll get into this again in a later chapter, but just to give you a flavor of it here, every atom, every element on the periodic table has an electronegativity value associated with it. And there are numbers, we can put quantifiable numbers on here. This is called the Pauling electronegativity scale. I'm not going to ask you to memorize these numbers, but I am going to expect that you know the trends, the periodic trends for electronegativity, where the most electronegative elements are found in the upper right corner, and the least electronegative elements are found in the lower left-hand corner. So the way this works for thinking about bonds is that if you have 2 atoms bonded together that are close in electronegativity, so either 2 of the same atoms, like these 2 carbon atoms, or a carbon and a hydrogen, those electronegativity differences are not very much, and so the electrons in the bond between are shared more or less evenly, and that bond can be considered nonpolar. If you have a little bit of a difference, like a kind of a significant difference, like oxygen at 3.5 and hydrogen at 2.1, these are then polar covalent bonds. The oxygen in OH and the nitrogen in NH, also all of the fluorines, if it were like a fluorine carbon bond, for example. These highly electronegative elements are called electronegative because they're more comfortable carrying that that negative charge of that extra electron density. So the difference between, say, an oxygen and a hydrogen is big enough that the electrons are going to tend to hang out over near the oxygen more of the time, or hang out over near the nitrogen more of the time. And then finally, if the difference is large enough, if you're talking about the first and sometimes the second row of the periodic table compared to the seventh row of the periodic column, you're talking about the first and second columns of the periodic table trying to bond with an element from the seventh column, those differences are great enough that it's an ionic bond sort of a situation. Okay, so how do we think about this with respect to carbon? I want to put carbon on the map for us and kind of frame everybody's thought processes around carbon, because it's organic chemistry and carbon is really important. So here's the elements of the second row of the periodic table, except for the inert gas neon at the end. Carbon is kind of right in the middle, right? So carbon is, it has 4 valence electrons. So it's not really gonna, give up or get any in an ionic way, because it would be too far away to get to a full valence shell. So it's very kind of amenable to making covalent bonds with other molecules. It plays well with others, right? So most of the bonds that carbon is going to form with other things are formed by sharing electrons in a covalent sense, either polar or non-polar, depending on what the other element is. And because of this, it's this capacity of carbon to form mainly covalent bonds, and this capacity of carbon to be comfortable accepting some electron density or giving some electron density, that makes it such a special element and so prevalent and so useful that it's become the building block of life, or one of the building blocks of life, and certainly a key element in organic chemistry. Okay, so here's a whole slide so that you guys know exactly how important the octet rule is. It is a whole slide. This is all that's on this slide. Nothing else is going to pop up. This is literally just me reiterating to you guys that the octet rule is important. It's going to help you understand where electrons are, how many electrons there are, where to put them in a molecule if there are any in the molecule you can't see. It's a really, really important rule. If you break the octet rule, if you have 10 electrons around a carbon atom, that is not good. You cannot, it's actually not possible to have more than 8 valence electrons for the second row of elements of the periodic table. There's no place for those to go. So if we're talking about building organic molecules and looking at organic molecules, we really want to stick to the octet rule as much as possible wherever we can. There are going to be a few occasions where an atom will not be able to get all the way to a full valence shell. It'll have less electrons than a full valence shell. And we'll talk about those special cases. But it cannot, in the second row of the periodic table, none of those elements can have more than 8 valence electrons. That's what I mean by breaking the octet rule. Okay, any questions about octet rule, or can we move on to Lewis dot structures? I'll try to slow down a little bit, but we do have to get through the material. So if you have questions, yeah, go ahead. Someone's raised their hand.
I just wanted to make sure I was understanding correctly. So you said that the carbons can't give and they can't accept electrons. So the only way that they can reach their octet is by sharing, right?
Yeah, so they do give and accept, but in a sharing way, not in an ionic, not in a full giving way, typically.
Okay.
Yeah? Okay. All right. Let's go on to Lewis dot structures. I'm going to call these Lewis dot structures and Lewis structures interchangeably. And what this is a tool that chemists have developed that allow us to talk to each other and draw out for each other where electrons are expected to be in molecules. So it's a way to illustrate bonding in molecules. And in order to be able to use this, we have to think about where the electrons are we have some tools to do that. And then once we get used to doing this and get used to seeing the molecules that are drawn, I don't know about how your all's experience is as you're just learning organic chemistry, but I've shown you a bunch of different organic molecules. And right now those pictures don't probably really mean anything to you in terms of the shape or in terms of where electrons are. That's all about to begin to change. We're going to start in this chapter trying to be able to make a connection for you guys between where the electrons are in a molecule and that kind of two-dimensional drawing that you've seen on the pages. And this is the beginning of that process. So I'm going to teach you guys today how to draw Lewis structures, and we're going to get some practice at it as well. It's a stepwise process, as much of science is. And so here are the steps. In the first step, you're going to identify how many total valence electrons there are in your molecule. Oh, and one thing I want to say, in terms of taking notes for this class and a good way to kind of like keep up with me while I'm going through the slides, I have the slide number in every corner. And you know that these slides are going to be posted for you guys after class. So one of the recommendations that I have for you guys is writing down the slide number as you're taking notes and not trying to write every single word that you see on the slide, but just write keywords, key phrases for yourself, some trigger to help you remember which of the things, what I was saying and what's important. But don't forget, you're going to have these slides at the end. Okay, so back to how to draw Lewis structures. Step 1, we're going to figure out how many total valence electrons there are in your molecule. Step 2, we're going to put the atoms in the physical order that we expect them to bond in. I'll talk more about that during some examples. It'll become more clear. And then in step 3, we're going to put the electrons into that molecule. We'll start by putting single bonds between all of the atoms because it's a molecule, so we have to have bonds to keep it together as a molecule. And then whatever electrons we have left over, we'll figure out where to put them. We'll either put them in as lone pairs associated with just one atom, or we'll put them in as multiple bonds. So if it's a double bond or a triple bond. So let's see some examples. We're going to start by looking at methane, CH4, which is the simplest organic molecule, simplest carbon-containing molecule. So step 1, identify how many total valence electrons are in your molecule. Well, how do we do that? Our valence electrons have to come from somewhere, and they're coming from the atoms that are making up this molecule. So how many valence electrons does carbon have? Everybody should be able to get this based on the brain exercises we did at the beginning. 4. Yep. Carbon has 4 valence electrons. And how many valence electrons does each hydrogen atom have?
1.
Okay.
So 4 in total.
So 4 in total. I'm trying to figure out, it looks like we've got some annotation on the screen. So let me.
Oh yeah, I think it's me.
That's okay. I just took it off. No worries. Okay. So, sorry, I gotta get my laser pointer back. All right. So we've got 4 valence electrons coming from carbon and 4 electrons coming, 1 each from each hydrogen atom. So we have 8 total electrons in our molecule for the valence shell. Next thing we're going to do is arrange the atoms in this expected bonding order. Now this is going to be something that takes time for you guys to get to know, but you'll eventually, there's really no way to teach a hard and fast rule, but you'll get to know it with time and with practice. Typically, you're going to have a central atom surrounded by some hydrogen atoms. Hydrogen atoms, for the purposes of this class, can only be bonded to one other thing. So you're only ever going to have hydrogens coming off of something. They're not going to be connected in a chain, for example. So I've gone ahead and done that here for methane. We're going to have a central carbon, and we're going to have 4 hydrogens around it. Okay, take a moment and think about this for yourself. If we have 2 electrons in every bond, and we have to follow the octet rule, we're not allowed to break the octet rule and go beyond 8 electrons for each atom. That means that no atom can have more than 4 bonds around it, right? So we're okay with methane because we have 4 bonds around this carbon. Well, we don't yet, but we're about to draw them in. But if we had CH5, we would be in real trouble because we wouldn't be able to figure out how to connect those atoms. I'll come back and talk about that again in a little bit. That might not make sense just yet. Okay, so we've done number 2. We've arranged the atoms in the expected bonding order. Someone has noted in the chat that the octet rule doesn't apply to hydrogen. Technically, the octet rule does not apply to hydrogen, but the fundamental concept behind the octet rule, that all of the atoms are trying to get a full valence shell or an empty valence shell, applies to hydrogen still. So hydrogen is aiming for 2, but the duet rule just doesn't sound very good. So we only really use octet rule, but with hydrogen, you just have to remember or know that hydrogen is aiming for 2. And someone else has asked, why is hydrogen 4 and not 1? So each hydrogen is 1, but we have 4 hydrogens in the molecule. So that's where we get 4 electrons. So it's a little bit weird to see, but it's hydrogen at 1 electron each, and there's 4 of them. So that's 4 electrons coming from all of the hydrogen atoms in the molecule. Okay, we've got number 2 down. Let's go ahead and do number 3. Arrange the electrons so that 2 electrons are in each bond, and as much as possible, all the valence shells are filled. So let's go ahead and do that. The way we're going to do it for now is to put 2 electrons in between each pair of atoms, right? So in order to build a single bond between carbon and hydrogen, we need 2 electrons in that bond. So we're going to put 2 dots between the carbon and the hydrogen. We're going to go through and do that for each of our carbon-hydrogen connections, right? We need to have those bonds there to make those connections. Okay, now we're going to figure out, have we used all of our electrons? And if not, we'll deal with that. And then we're also going to double check, how are we doing on filling our valence shells? So first, have we used all of our electrons? Well, yes, we had 8 electrons that got brought into the molecule by each of the atoms, or by all of the atoms in total, I should say. And we have used all 8 to form our bonds between carbon and the 4 hydrogens bonded to. Okay, so that's great. We don't have any extra electrons. We'll see an example where we will have extra electrons, and you'll see how to use that, what to do with that. So the next thing, as much as possible, all valence shells are filled. Okay, so every hydrogen here is counting the 2 electrons next to it when it's counting its electrons for its valence shell. So every hydrogen here has 2 electrons, so they all have a satisfied valence shell. And the carbon in the middle has 8 electrons that it's counting towards filling its octet or its valence shell. And so it has 8 electrons that it's sharing, but it still can count those towards fulfilling the octet rule. So we are golden. And this is a perfectly acceptable Lewis dot structure for methane. Okay, let's try some more. Oh, before we try some more, I think that from this step 1 here, you guys can already see here that we're going to need to know our valence electrons. So I'm going to just drive that point home. And for the question in the chat box about the line, I'll get to that in a couple of slides. So we're going to know our valence electrons. There's the chart that you can refer to, but more importantly and more readily, you can get this information from the periodic table. Eventually, you'll just remember the ones that you use a lot because you're using them a lot. But if you don't remember, you can read the number of valence electrons off of the periodic table. Okay, so let's go ahead and do some practice problems together. And for right now, I'm going to be using 2 dots to represent a bond. We will switch to lines, so just hold your horses on that stuff. But for right now, we're going to use 2 dots so that everybody can really make sure that everyone can really make sure that they are seeing all of the electrons in this process. Okay, does anyone have any questions before we do these examples?
Yes.
Go ahead.
So my question is, how are we gonna identify what's the central atom? It's always written in the first place, in the first position, or is it based on the more valence electron in that molecule?
Yeah, so this is a difficult question. Thank you for it. You'll start to get to know how molecules are laid out and how atoms are laid out in molecules. But sort of, yes. So, hydrogens can each only be bonded to one thing. So in the case where there's a lot of hydrogen, they'll have to be bonded to some other atom that can then bond to other things, right? So you'll see, and you'll pick this up just from experience and seeing things, but yes, usually there's a central atom that has, it doesn't have to be necessarily a higher valence number of electrons, but a central atom and atoms around it. Let's try some more examples, and I think you guys will see. So for nitrogen, what's the valence electrons in nitrogen? How many do they have?
5.
Okay, and we've got 3 hydrogen atoms, so that'll bring in 3 valence electrons, 1 from each of the hydrogen atoms. So we got 8 electrons again here. So when we put our atoms in bonding order, we know hydrogens can only bond to nitrogen because they're able to build a molecule. So we're going to put nitrogen in the middle and hydrogen on the sides. And when we do that, and we fill in our 2 dots between each nitrogen and hydrogen, that'll use up 6 of our electrons to make bonds, right? We need to make 3 bonds here, 3 bonds between nitrogen and hydrogen. So that'll use up 6 electrons. We have 2 electrons left over. Well, where do those 2 electrons go? So we have to choose, are they going to be a lone pair or are they going to be an extra bond? And in this case, before we had put in this lone pair, you guys see the answer already, going in as a nitrogen lone pair. And the reason is because before we had put those in, when we only put in the bonding electrons, nitrogen would only have 6 electrons. And in order for nitrogen to achieve its octet, it would need 2 more. And lucky for us, we have 2 more. Reba, do you still have a question? Your hand is still raised. I can't tell.
No.
Okay. Okay. So here are some other examples that you guys can try. We'll go through these together also, but I want to give you guys a chance to think about it on your own first. So go ahead and think about the valence electrons that are going to be present in each of these molecules, and then go ahead and try to draw it out, and we'll go through it together. Okay, so for oxygen, what's the valence number of oxygen?
6.
6.
Okay, good. You guys are getting really used to this. I like it. So yep, it's 6 electrons that oxygen is bringing to the table, 2 electrons that each of the hydrogen atoms are bringing to the table. And when we put our atoms in order, we're going to put the oxygen in the middle so that each of the hydrogen atoms can be bonded to it. And we'll end up using 4 of these 8 electrons to create the bonds. 2 between an oxygen and one of the hydrogens, and another 2 between the oxygen and the other hydrogen. We'll have 4 electrons left. So what do we do with those 4 electrons? They become
A lone pair.
Yeah, great. So here you've got the Lewis dot structure for H2O, which is water. So some of you might be thinking to yourself, well, water is bent. Don't worry about geometry for now. For now, the Lewis structures that we want to get, the point of the Lewis structures for now is for us to have a sense of which atom or atoms each pair of electrons belong to, right? So this pair of electrons here belongs to both the hydrogen and the oxygen, but this lone pair of electrons belongs only to the oxygen. So that's the question we're answering right now. What about for chlorine? How many valence electrons does each chlorine atom bring?
7.
Awesome. Great. So each chlorine atom is going to bring 7 electrons to the table. That's 14 total. How many electrons are going to be used in a bond?
1 from each.
2, 1 pair, right? So we're 2 atoms. So there's only one way to put these atoms into a bonding order. We're going to put them right next to each other. We'll put 2 electrons into the bond between the 2 chlorine atoms. What that leaves us 12 electrons. What do we do with those 12 electrons?
Lone pairs?
Lone pairs, that's right. That's 6 lone pairs. So we have our chlorine atom here with the 2 electrons in a bond together, shared between them. So these 2 electrons in the middle are shared. And then each chlorine has 3 lone pairs or 6 electrons that it's not sharing. And if you add up all the shared and unshared electrons, each of these chlorines will have a full octet. Okay, let's keep going. So here, this answers the question about dots versus lines. Let me back up a little bit. Someone has asked about chlorine. Why wouldn't a triple bond work? So if you were to, you can draw this out and answer this question for yourself. If you were to draw out, chlorine with triple bond, then you're using 6 electrons here, right? That means you have 8 electrons left in the system because you have 14 electrons total. And so we have 8 electrons left in the system, but we can only accommodate 1 lone pair on each of these chlorines, because if we go beyond that, we would break the octet rule, right? And so that means that in order to preserve the octet rule, we can only fit 10 electrons into the system if we have a triple bond here. And when you do that, you have 4 electrons left over and you have nowhere to put them because your octets are full. So that does not work. Did that answer your question? A lot of times you can see these things when you try them out, but the easiest way to do this, until you get comfortable and you get to know things, the easiest way to do this is to put in a single bond and then put in lone pairs until the octets are filled, and then go back and think about multiple bonds. Okay, let me get my pointer back. All right, so we've been looking at Lewis dot structures, but I want to switch everybody gently and slowly over to Lewis structures. So for the question about the triple bond, I want you guys to just try it out for yourself, and I need to move forward now, but think about it after class on your own, and see what happens to the octets when you try to make a triple bond. You can't get full octets and use all of the electrons. Okay, so, yeah, go ahead. No? Okay. We've been looking at Lewis dot structures where we've been representing the bonding electrons as 2 dots between 2 atoms because each dot represents an electron. In this class, I want you guys to start getting accustomed to using a line or a dash to represent a bond, and that's going to show you how you, that's going to represent the 2 atoms that are in a bond. Lone pairs should still be shown as dots. So I've given some examples here of Lewis structures that show all of the electrons. You'll see in each of these structures, every atom has a full octet. Some atoms have lone pairs to be able to get their full octet, but all of the bonds are shown as lines instead. Okay, the other thing to mention here is that really you have to do practice problems to get comfortable with this. And I wanted to put this up here because this is a chart that shows about common bonding patterns for some of the more common elements that we're going to be using in organic chemistry. So what this means, your book calls this a valence. What this valence means, and I don't like that they call it a valence because I think it's confusing with respect to valence electrons. This means the number of bonds that that element prefers to have, or that type of atom prefers to have. So for carbon, that number is 4. It could be 4 single bonds, as shown here, or 2 single and 1 double, or 1 single and 1 triple. And you can see each of these other ones has a common preference for number of bonds formed that'll fit this type of pattern. I don't want you guys to memorize this. It'll come to you naturally from practice doing these molecules and following the octet rule and the method for drawing Lewis dot structure. What I do want to make sure everybody notices, if you're looking at this chart, that this valence term that your book is using is the number of bonds formed and not the same as the number of valence electrons. So I want you guys to fill in this row of this chart on your own after class for the 5 elements when you're reviewing your slides. Okay, I want to quickly get to our in-class participation for the last couple of minutes. So I'm going to show you this slide briefly and we can get to it on Wednesday. Most of our Lewis structures so far, we've seen only single bonds and lone pairs, but we can also have multiple bonds. And if we have 2 pairs of electrons or 4 electrons total, that's a double bond. And if it's 3 pairs or 6 electrons total, that's a triple bond. But again, one line represents 2 electrons always. Later in the chapter, we'll get into what these mean structurally more. But for Lewis dot structures, every line represents 2 electrons. And the way you decide between lone pairs and multiple bonds is by following the octet rule and trying to satisfy the octet rule for every atom as much as you can. Okay, so we've got an in-class participation. We're running a little bit behind schedule, but I'm gonna put this whole thing up so you guys can take a look at it and try to work through it, and I'll stick and answer questions. These are 3 questions that I want you guys to answer. And what you're going to do is you can use your own sheet of paper, or if you prefer to take a screenshot of this and electronically write on it, but you're going to upload your work to Canvas by the end of the day today. There's an assignment for this under the assignments tab that went live at 1 o'clock. And basically, this is your chance to try these out on your own and get some participation points for it. So go ahead and be working on these, and I'll talk a little bit in the background about participation points and how they work. Participation points are for effort. So if you come to class and if you try to answer the questions, and if you upload it in a timely fashion, so by the end of the day today, then you will get full credit for participation. If you don't get it in before the end of the day, you'll get partial credit. So can you guys make sure your microphones are muted? Unless you have a question.
I have a question on the assignment.
Yeah, go ahead.
I loaded Campus right now to see the assignment, and you said it was live at 1 o'clock, but I can't find it.
Check under the assignments tab. Do you see it there?
I don't think so. I might just have to refresh my page. But in the chat, it's also saying like other students.
Yeah, okay. Well, I'm gonna leave this up for you guys to be looking at. I'm gonna try to log into Canvas on my phone and see if I messed something up on the Canvas settings. Thank you for letting me know. And
no problem, thank you.
If it's not up now, I'll get it up like ASAP after class. Someone's asked about when we'll get the answers when I'll give the answers to this. It's gonna vary depending on the participation assignment. Sometimes I'll present it at the next class. Sometimes I'll host it. But basically, if you haven't turned it in on time by the deadline and you're turning it in late, you'll get partial credit for turning it in late, and you'll get less partial credit if you're turning it in after I've posted the answers. Does that make sense? So it's to your benefit to come to class, and it's to your benefit to turn in the participation assignments on time. Okay, my phone's not letting me log into Canvas, so I will fix this. I will fix this ASAP so that you guys can post your things. I'm gonna post the slides so you'll be able to see the question, the slides. That should be up within the hour. Participation points are gonna depend on how many participation assignments I've given you guys over the course. And so I can't really answer that, but pretty much the way I've done it in the past, that all participation assignments count the same weight as each other. So then there'll be an average in the end. Okay, and someone wants to ask a question about bond polarity and electronegativity. I actually have to run today after class, so if you could put your question in an email to me, I would appreciate that, or hold on to it until the next class, either one.
Sorry, just real quick, someone asked in the chat, did you want us to write the whole question out, or is it okay if we just write 1, 2, 3 and then answer it?
It's totally fine to just write 1, 2, 3, and then answer that. I'm still trying to get into my phone and see if I can get this properly loaded for you guys. Oh, it's because I didn't publish it. All right, refresh your screens and see if you can see it now.
Yeah, I can see it now.
Yeah.
Okay, awesome. That's where you guys can upload it, is in the assignments tab. And thank you guys very much for your attention. It'll take me probably an hour and a half to get the slides posted. So if you want to take a screenshot real quick, please do. And otherwise, I will see you guys on Wednesday.
Thank you. Thank you so much.
Thank
Yeah.
you.
Thank you.